So we've talked about finding potentially counterparts for at other wavelengths for some FRBs. I just wanted to kind of just to get a sense of scale of what's feasible and what's difficult. One question, and I think we've talked about this a little bit, are gamma ray detections viable in these models where a large fraction of the energy actually comes out at other wavebands? Just to give you a sense, the gamma ray emission from GRB, it should be GRB, or GW 170817, was about 10 to the 47 ergs and was barely detected at 40 megaparsecs, just to kind of set the scale. And this is a plot from Ben showing the expected gamma ray fluences for, I think this is mainly localized events, relative to the detection threshold, and you can see that we're about 4 or 5 orders of magnitude off. In any case, in the optical, an energy, again, just to set a scale, an energy of 10 to the 46 ergs emitted in a millisecond is equivalent to about magnitude 21 at a distance of 100 megaparsecs in typical observations that are done as part of optical time domain surveys. So for example, for ZTF, that would be about a 3 sigma detection in a single frame. So not something that's very easy to pick out as a counterpart to an FRB. And these are at fairly small distances. Another point I wanted to pick up on is this question of host galaxies and the demographics. So again, just to give you a sense, the picture has somewhat changed with a few objects, and taking one of in phase lesson, I don't remember which number it was, about small number statistics. We're sitting in a regime where it might actually be quite difficult to definitively say what kind of channels are producing the sources as power FRBs, because it's starting to bunch up between things that only track stellar mass or star formation rate, or a mix of several different channels with 20% of this, 30% of that. So we're gonna have to see how that shapes up with larger numbers, but we're not sitting in one extreme or the other at the moment. Another point I wanted to make is that the discussion today between the talks about finding counterparts, looking at host galaxies, and then Brian's talk about using FRBs as probes, I think it's becoming highly reminiscent of many other fields in astronomy, type 1a supernovae, gamma ray bursts, quasars, where there's this kind of dual efforts to both understand the physical nature of these events, and at the same time, independent of our understanding of what they are, use them as tools for to answer other questions in cosmology, in black hole formation, galaxy evolution, and so forth. And it looks like the FRB field is kind of starting to enter that same approach and similar bifurcation of efforts between understanding the progenitors, understanding the emission mechanism, and using them as tools. I wanted to start with a few guiding questions, which I think we've touched on, but I really want to kind of push on these and get the panel members and the audience input on. So as a community, and by community here, I mean both the teams that are searching for FRBs and more broadly, people who are interested in questions related to these sources and in their use as probes, are we optimizing the potential for real-time and long-term follow-up observations with the current mode of observations and dissemination of information? What observational resources would be required to build the kind of FRB samples that are going to be large enough to answer the questions that we've been addressing? Both what the progenitors and the engines are, and how to use them efficiently as probes of the intergalactic medium and galaxies. So we're likely talking about samples of order 100 or hundreds of events, maybe even thousands. Is what we're doing now scalable to that level? What are effective ways to probe the nature of FRB engines by studying other astrophysical systems? And so we heard a little bit about this, looking at local magnetars as potential analogs or not, superluminous supernovae, gamma ray bursts, pulsars. How are we going to study these other systems in a way that will focus our understanding of what phenomena might be related to FRBs? And I wanted to kind of, in particular, we've been talking a lot about magnetars. So I wanted to just remind everybody of this famous quote from Shakespeare. That we call a magnetar by any other name would smell as sweet. So we just, I think, again, need to be cautious about what we mean when we talk about these kind of systems. Magnetar, neutron stars, when we're comparing galactic populations and extragalactic populations, when we're comparing them to other transients, we just need to be cognizant that different communities have different ways of defining things that we end up calling the same. So not to be overdrawn by that. So I just wanted to open this up to any of the panel members to pick up on any of these points and get going.
Observational question. So one of the things I keep forgetting. So one of the things that motivated so anyways, we talked about many magnetar models. I don't want to go into the details. One of the things that motivate us, thinking about whether the emission site is close to the engine or far away, is related to whether magnetars eject material. We've heard for the giant flare there was evidence from a radio afterglow that it ejected a lot of baryons, and if those were very frequent from magnetar flares, even of weaker energy, you could imagine making it hard for a radio pulse to get out from a heavily repeating source. So I guess it's a question kind of for Nando, which is, do we have any evidence? What do we have evidence for in terms of mass ejection from weaker flares besides the giant ones? Do we expect that if you have a flare, it would sort of black out the engine for a bit, or what is the evidence along those lines, if any?
Close to none, I would say. I mean, in the giant
meaning
flares,
we can rule it out, or
course,
meaning that it's hard to actually probe?
no, it's observationally hard, I think. I mean, one possible evidence might be, evidence. I don't know if we can call it mass eject, I don't know, or magnetosphere disturbing, or I don't know how to call that, which is the plot that I showed where you see the quenching of the radio emission during the bursts. Those are short bursts, so 10 to the 38 Earth per second, millisecond, 10 milliseconds, so very short. So there, in that moment, somehow the radio emission got quenched because of this burst. So something happened in the magnetosphere due to the bursts or connected with the burst that somehow had a disturbance of the radio coherent emission. Apart from that, from short bursts, I would say none that I remember. I don't know if Vicky remembers something, but
we have tried this many occasions. You have to get the X-ray and radio telescopes to observe at the same time, and you have to get the source to cooperate. And the source doesn't always cooperate, and that's in that case it did. The one that Nanda's talking about, it did. But that was not that was a high magnetic field radio pulsar where we saw that, and so that might not have anything to do with the sort of radio emission that you see in magnetar outbursts. It could be, but some people argue, like it was Maxime Ludikoff who was arguing that this was the radio emission that got quenched was the standard radio emission, not the outer magnetosphere radio emission that you think, or that's argued to be there in magnetar outbursts. So yeah, it's a Maxime argument.
And just to add to that, there are powered moding pulsars that show this as well, where the radio and X-ray are anti-correlated with each other.
But they don't show bursts.
No, they don't show bursts, but
that's different. This is
the Hermsen papers.
Yeah. This is mode switching, right?
Yeah, this is mode switching. Yeah. But
you can use it. I don't think it's exactly the same.
Sorry?
I don't think it's exactly the same as this case. I mean, this is also something, but...
No, that's true, but I think I agree with Vicky as well that this is not obviously the same case as what we're potentially talking about for FRBs.
The other thing is that you might hope that maybe when there's an injection of mass that you might... I'm wearing one. You might hope that there's something to see in the period or the period derivatives, but even after the giant flare, for reasons we don't understand, the period and the period derivative didn't show any evidence for having all that material blasted off. So even less likely to see anything in the timing for a smaller flare. But I don't know, Vicky, is there any timing behavior that's correlated with flares that you've seen?
Yeah, generally the P dots get very large after magnetar outbursts. They get the magnitude of the P dots very, and then you have a recovery period. So yes,
although it depends on the source. For example, what he mentioned, I mean, the giant flare of 1806 did not show large pitot changes. While, for example, 1048, that probably is the one it does.
Yeah, so I think 1806. That's probably, well, I think that's more of an exception. Like most of them, I think, show timing variations at the time of outbursts.
To get back to Brian's original thing, this is primarily, I guess, related to repeating FRBs, and we have seen separations down sub-second separations between some of these bursts, which we can still call independent bursts. So
that was my broader point: is if you're going to make the burst come from magnetosphere, you have to have a very clean environment,
right?
And so if one burst is making too much crud, then it's going to be hard for the next one to get out. And
that's right, and we've certainly seen sub-second separations between independent bursts for 121102 at least.
But, sorry, if it comes from the crust, you can have sub-second separation into different regions of the crust where you stress, and you have a flare from one kind. The trigger comes from the crust, not the.
Right. Yeah. I think you can get flares that quickly. I guess it's a question of whatever that mechanism is. Does it get quenched if there's too much material?
So what happens if for intermediate flares, for example, we know that they're more frequent. Is there mass ejection for?
Can you turn your microphone on?
Oh, sorry. I thought I turned it on. So what happens for intermediate flares? So they're more frequent. Is there mass ejection at that time? So.
Let's define what you mean for mass. What you mean for mass ejection. If mass ejection, if evidence for mass ejections mean that we see a radio counterpart or an expanding shell, no, we don't see it because I'm not sure they were all observed deep enough and good enough to say if there was or not. So, no, not for the giant flare of 1806, yes. For the deep, more normal bursts, there are no other evidence of this kind. But I'm not sure we can really put a limit on this because the observations are very sparse.
So let me push, so we don't spend all of our time talking about magnetars. Let me push a little bit on point number 3, which is somewhat related of how do we make potential progress on FRBs by studying other astrophysical systems. So let me make a concrete suggestion, and maybe people can tell me if it's crazy. But now that CHIME is finding so many FRBs, we're not lacking for statistics, and ASCAP is finding localization. There are enough localizations coming in. Is there any reason not to spend a lot of telescope time on some of the other facilities staring at other types of sources that we might suspect to be associated with FRBs as a way of actually seeing if we can, you might as well, if you're going to point somewhere on the sky, why not point where there was a GRB 10 years ago or a superluminous supernova or something else? So any thoughts on that?
I guess audience or?
So one of the obvious difficulties and the thing that always gets you a loophole, like if you don't find anything, is this apparent clustering of the bursts. It's very extreme for 121102. It's maybe unclear for example, CHIME, how strongly clustered in time they are. But if you have any sort of clustering, you can always just invoke, it's extremely highly clustered, or we just haven't, you really have to observe substantially longer than Poissonian, but Poisson statistics would suggest make any sort of meaningful limit. So it is difficult.
Yeah, that's fine. But if you're finding FRBs, let's say with parks, by pointing somewhere random, just saying you can point at that random place and get FRBs anyway that are not related to the source.
I agree. If you have time and you need to point somewhere, you may as well point somewhere where you can look for repeats. That's
the flip side of that, though, is that with enough exposure, given that these single-dish fields of view are large, you will pick up FRBs by chance.
Right. Sure.
Sure, but you know the positions well, and so you can always follow
not
up.
As well for parks or
No, I mean the position of the sources and the redshifts are known in advance, and so if you see something, then you can go back and see if you find repetitions, and you're not starting from nothing.
Right. But just sky exposure, given the rates, you can predict that in a survey of 100 hours, you will pick up N of these by chance, Ryan.
I think the obvious instrument for that is fast, though. Right, you want to take the most gain you can possibly get if you're going to go and try to do this, and it's going to sort of help with Laura's issue of intermittency as well, because you're going to see more fainter pulses.
And the smallest beam of the
smallest beam,
set, yeah.
Well, can anybody say what strategies FAST is using? Who presented the FAST result the other day? Was that Bing?
Bing.
Sorry. Do you know anything about the strategies that FAST is using? Like, is it doing targeted searches or blind searches and looking for fast radio bursts?
Blind search just started because the field is small, so the chance is low, but it seems to be consistent with the prediction. The rate is similar to Parkes, for example. The very first one, I think the DM is relatively large, about 1,000, which is also consistent because you can see deeper, you can see farther distance, but with a smaller field of view. So it seems to be consistent. And for targeted search, of course, the 121102 has been monitored for a while, and for the others, it's just looking at the properties of the burst itself and see. It's just a guessing. The one I showed yesterday, it was purely just based on luminosity. It looks like it's a relatively low luminosity, consistent with repeaters, and we just went there, and there are a lot of repeating bursts. So there's a plan of following some of the other candidates. We don't know whether we can catch more repeaters.
Ellie?
I actually want to make two comments. One, in your previous slide, I think you are depressing the field. So if you can go back to your previous slide. And on this previous one, yeah, so 10 to the 46 ergs is 21 magnitude it's okay. So I think it is 21 magnitudes at larger distances. So I think you should. I think it should be possible to see such things with ZTF, but certainly with let's say LSST, should be able to see them to further distances. So I think that trying to see with the optical telescopes, something like LSST, it should be a doable thing, and it would have a wide field of view. And if you have 1,000 bursts per day on sky, and it sees them to several hundred megaparsecs, there should be a possibility to see them on. So this is one comment. The other thing is that I think that a very important thing would be to detect the nearest FRB possible. I think this is probably the most promising thing to do, to find the nearest one, and then hammer on that one. But for this you need wide field, shallow surveys rather than very deep.
I mean, part of the issue is that ZTF surveys are 30-second exposure, so if it's really a millisecond, you're averaging over a long time. But you could use Tomoe goes in at a half second. You could use Ultracam at a millisecond, and then it's much easier. So.
The same vein, I would say keep observing the same source has a lot of virtue. So I have a question. For example, if the repeater keep repeating for the next 10, 15 years, what's the prospect of getting the underlying rotation period using the same technique that we do for red, for example? Is there a prospect? Is there a prospect getting that?
I can comment on that. I mean, there's this.
If you have a lot more data in 10 more years, is there a
without
prospect?
A lot more data, there's the breakthrough listen observation, for example, where there's over 100 bursts in a 1-hour period. And you don't have to worry about linking those observations across different sets or coherence. You know that that was a coherent data set. There's 100 bursts in a 1-hour period, and we've searched it pretty exhaustively. And if you allow for a short enough period, like a millisecond, then yes, sure, you can say it's a millisecond period, but that's not saying much. If you allow for any kind of epicycle, like an orbit period or a wide emission phase, then you can fit those bursts. But otherwise, no, there is not a periodicity that's obvious there. And I don't think that more bursts from FRB 121102 will ever improve that particular aspect of it, of an underlying periodicity.
Here is like seconds, something.
Yeah, but we have 100 bursts in an hour. It's not going to get any better than that as far as this technique goes. I mean, others might disagree with me there, but.
Yes.
So I want to make a comment that I would suggest that not doing the occurrence time series as the periodicity search, do the PA, do the polarization angle, which should be modulated by the rotation instead of the occurrence.
Could I
Yeah,
maybe bring it to the other end of the spectrum of instruments? And I wondered, would it be useful or possible to do, rather than focusing on like ZTF, LSST style, really wide, expensive, big instruments? If I feel like, at least in the gamma ray, they've kind of moved towards a CubeSat direction of instruments. Would it be reasonable to try to do that with FRBs, where you have a very small, very inexpensive instrument, but it's, maybe it can't do as well as a bigger thing, but it can be paired with a radio interferometer, and then you catch all FRBs in real time? Is that something that would be useful?
At what wavelength?
X-ray, gamma. I mean, I know we already do this in the gamma rays. I don't know if there's any CubeSats in the optical yet.
There are CubeSats in the optical, but I think the challenge is just getting enough photons. So you need a large collecting area both in X-rays and optical. So if you just get one photon in a millisecond, are you sure that it is associated with that FRB? It's really hard.
But if you could catch them all, literally every FRB that you see, is that,
yeah, you could,
would those
statistically
limits
add
be
up.
more useful than just small statistics on a few?
Maybe you need, I guess that at least that it was for GRBs. Before that, you need one detection. So you need to be sure they emit in that band, and then you go for the population. But going blind, it's a bit, nobody will fund it, I'm afraid.
So let me, again, connect this to the first question, since there's a lot of discussion here of possible resources that are around that can do some of this work of follow-up. Is there a general sense that the way things are happening now is good enough and we should continue this way, or that a change in philosophy or mentality or pace would be helpful, opening things up more than they are now?
I have I was just thinking about point one as we were sitting here, but I was just thinking about ways to, I think a common theme yesterday and today has been that localization is really important, whether it comes from the FRB itself or, from any contextual information from where the FRB happens to be sitting with respect to galaxy catalog. So are people thinking about, for instance, utilizing LSST and the photometric redshifts that whole catalog will provide to cross-correlate it with, for instance, the arc minute positions that will be coming out. And I think thinking along those lines will, how to basically localize these events and use all the resources possible that will be available or coming online in the future is going to be a healthy thing.
Yeah, so I would just add, so along those same lines, I wonder if CHIME is doing anything currently, given that they see the whole sky. Are there any kinds of cross correlations going on with, positions of other transients or?
Yeah, so I don't know if Kendrick is around, but so there is a student, Masood. His student Masood is working on 2D cross correlations of FRBs with known galaxies. It's obviously hard because you need to know the positions and everything reasonably well, and so it's been worked on. It's being worked on, not been worked on.
It requires a population of sources with known redshifts. So LSST would be useful for photometric redshifts in general, but I don't think there's enough power without a spectroscopic sample to do those types of 2D correlations. Yeah.
I believe for the real fast one that Casey showed, they are using photometric galaxy catalog.
No, it's not a photometric catalog. It's a photometric redshift from the imaging data that exists.
Okay.
But Sriharsh, it seemed like from the theory paper that they wrote, the forecasting paper, all they needed was 10 to the 3 sources with arc minute resolution, and you already get a pretty good constraint on the redshift distribution of FRBs. So presumably you guys can already do this.
Yeah, I'm not an expert on this, but perhaps Daniele wants to add something?
Yes. At the moment, most of the sources, as you can see in the papers, are localized at tens of arc minutes with CHIME. So we are doing some, Masood and Kendrick are doing some preliminary studies, and on on my side, we are trying to improve by using the raw voltages, the localization down to 1 arc minute. And at that point, you can really have like a cross correlation that is meaningful. But it's a work in progress, so it's going to take still a few months.
Sorry, well, just to confirm, so it sounds like this is cross correlation with just galaxies and trying to match the DM inferred redshift with.
Yeah, I'm not sure about the detail of the correlation, but yeah, it's like correlating structures in the universe with distribution of stereo burst.
I see. Okay.
Okay, we have a question there.
So I don't understand something. Maybe you can clarify it for me. So Levin here is saying that the magnetars in the galaxy are like 1,000 years old. Assuming democratically, meaning everybody thinks that these are magnetars, FRB 121102 is at about a gigaparsec, correct? I would assume that magnetars are at kiloparsec. This gives me 10 to the power 12 in luminosity, while in the age it is only a factor of 30. So it is unthinkable to someone naive that a factor of 30 can get you down 10 to the power 12 in terms of luminosity. And I would assume that your chime or something, isn't it routinely observing magnetars? Shouldn't it have detected a magnetar? So it's 30 to translate it into 10 to the power 12 sounds funny.
Well, that's why we didn't think FRBs existed in the first place. Because we saw pulsars and we thought this can't be the same thing. Because there would have to be at this amazing distance. So it has to be something different.
But yet today, by popular vote, is magnetar. We have a magnetar.
Yeah, that's just because the theorist just turns knobs until they can't turn them anymore. So it's a millisecond magnetar. Because what else could it be, right?
But Andre,
you haven't got any other knobs to turn.
Andre, you're just proving again the worth of popular vote.
Yeah.
To be fair, of the 12 orders of magnitude, the magnetar bursts are much brighter than FRBs. So you get like maybe, I don't know, 10 of those orders of magnitude back.
No, but what I think what he's saying is, yeah.
Oh, sure. Oh, sorry. Milliseconds. Okay, without scattering measure, they should be even shorter.
Wait,
The
so do you mean
millisecond
shorter or
pulsar
fainter?
names. Millisecond pulsars are excellent pulsars.
Nah, don't do anything.
No.
Isn't it strange?
Well, okay, so I'll just, number one, we're in the northern hemisphere. Most magnetars are in the southern hemisphere. But there are there are some magnetars in the northern hemisphere, including ones that have recently been an outburst, and we haven't seen anything from them. But I think, yeah, the argument has always been that the magnetars that are in FRBs are special magnetars, not but yes, and I think your point is very well taken. I mean, that's exactly what we were saying a little earlier.
It's trivial among professionals.
No, you're not understanding what I'm saying. I'll repeat. I agree with you. Full stop.
I think it's
Somehow we've been drawn back to magnetars.
I'm sorry. I have to respond. No, not all. I mean, there are some magnetar models where there's no memory of what's going on around it. The magnetar models that we've developed and the ones that Andrei Belibrov developed rely critically on the fact that these magnetars have been flaring at a much higher rate. So there's a material ahead of them for these shocks to run into, or there's a pulsar wind that's more powerful than the old magnetars in our galaxy would produce pulsar winds. So it's not just a matter of the flare makes this radio emission. There's something having to do with how active the source is. And so maybe this very short period of time early in a magnetar's evolution where it's actually, active enough to create the medium ahead of it that's going to make FRBs possible is what I'm saying. Yeah, we could talk about it. Yeah.
Can I comment on this a second?
I want to. Okay, go ahead.
I can pull you back to the second question if you want.
Yeah, and I wanted to get to your slide too.
That's fine. If I remember, the second is do we have to do things qualitatively different going forward? I think if the first 10 that we've identified and localized are representative of the next 100, I think probably not. That is to get host properties on even at rates of 100 per year. That would be feasible. The ones that do give me pause are the ones like Professor Fong showed, where you don't see anything in the location. And I think of the 10, there's probably one that gives me some pause.
I was going to say the false positive rate that Tana showed, 10% false positive rate. I mean, of the 10, one is wrong. And certainly I would be willing to bet which one that one is.
And so then the question is, how much resources do you put into those 10%? And from my own perspective, I'm as worried about the biases that are leading to the FRB population as much so as I would be towards the biases on the follow-up effort. So there needs to be work on certainly on both sides of understanding what is the population that we do get to follow up, and then what are the ones that are either being falsely identified or just very difficult to the point where you don't make a secure identification.
So just Jason, to push back on that a little bit. I mean, when we again look at the example of, let's say, GRBs, long and short GRBs, it took well more than a couple of decades to build up samples of order 100 host galaxies. It's not because there was a lack of sources to follow up. It's just building up the resources of the community and devoting it while other things are happening at the same time. So I'm not convinced it's trivial to do 100, but
yeah, it's of order an hour a source. It's 10 nights of data. It's not that much. Honestly, but that's for the easier ones. Again, the 10% that are challenging, that could easily burn you another 10 or 20 nights.
And then there's HST and ALMA and all of this. Yes, Ellie?
So you were asking about things that might need to be done differently. So it's not clear to me whether there is a coordination with optical observations in overlapping fields that would reach significant relevant sensitivity with radio efforts. Because in principle, this is somewhere where you can really improve maybe you detect something, and if not, you really improve the current limits that you have. But if there is no coordination with suitable optical observatories, then
yeah, I was just going to reiterate what Ido said earlier, is that while LIGO has been a little bit boring for EM observers, O3, I should qualify, all that infrastructure is in place, rapid follow-up or cross-correlation with any type of data stream you can imagine. And so I think that's really a great resource that this community could tap into in terms of communicating with that community observers. Of course, there need to be some guidance as to on what time scales, what wavelengths, that type of thing.
There is a significant difference here, because the LIGO follow-ups for neutral star mergers, whatever, the optical emission would last for hours and days.
Yep.
And this is something completely different. We don't know whether there is an afterglow at all, and I think it would be best to have a simultaneous radio and observation of the same field, because if it is a short event, you don't want to miss it. And it's doable. You don't need big telescopes for that, as also Stero said. But if it's not coordinated and it will not happen, I think you would be missing a possible significant way to make progress.
But I mean, it would help to switch it out with the electron multiplying CCD, which would just read out at a millisecond for. I don't know whether somebody's looking into it, but that would be really nice.
I don't know if anyone's working on that because it wasn't really built for FRB, so it wasn't for short integration time. So.
Vicky was
so how well, so there's a question, how well characterized is the optical variable sky on millisecond timescales at the wavelengths that, yeah, okay, so I see.
Yeah, it's not very well characterized. Also, if you're just doing image subtraction, then the scintillation and atmospheric effects themselves are going to cause false positives in there.
Yeah.
I was just going to say, so there is, I believe, 30 nights of data at 1 millisecond read time with roughly half-degree field of view from the 200-inch staring at M28. So it was looking for Kuiper belt occultations of stars in M28, but it's a huge field, it's millisecond sampling, and it's at least 30 nights of data. So one could get something from it, I think.
I'll make a quick comment about the follow-up business that unlike the GRB case, the radio signature comes last. And so it's not that you can trigger on the radio, you'll have to be taking data before you get the radio trigger. And sometimes, particularly at lower frequencies, those delays can be very substantial compared to the higher energy signatures.
There is a nice project led by Jeff Cook out of Swinburne called Deeper, Wider, Faster Survey, where he is coordinating radio telescopes and optical telescopes but only for over a couple weeks per year, and he needs to get lucky.
Yeah. Yeah, to do the experiment you propose, you also have to have an instrument that's matched the field of view of your radio telescope, which is that's the big challenge. If you're not going to try to be lucky, right? If you're trying to or if you're staring, yeah.
Right. So I would like to come back to the point which Ellie made and sort of ask a question to the theorists in the group. Are there expected to be afterglows at any on any energy scale which would be visible for the low DM FRBs? So is it worth going after low DM FRBs with optical telescopes and trying to find afterglows on a few day or a week time scale? I mean, hours is possible, but seconds is really hard, right? So you can't slew Palomar in a second, but few hours it's possible. So is it worth setting up a logistics chain so that we can get a localization for a bright low DM FRB and then?
Maybe a way to rephrase this question, where FRBs are extremely, common in the universe. So if you said everyone made it an afterglow you could detect, you'd have to make sure that was consistent with the fact that we haven't seen these things blindly as something else.
So that's why the constraint on very low DM, which would be nearby and detectable or something.
Right. So I'd like to be able to establish that if we have different types of transits, we can establish they don't make FRBs. But, it would be amazing. But I think the rates of FRBs are high enough that we couldn't have too common of a bright thing. But I'll let other theorists opine.
Yeah, Vicky, did you want to say something?
To say, one of the reasons that we prioritized pushing repeaters quickly was exactly so that people could start following them up. And plus, we are in the process of finalizing our public webpage where you can go for any of those repeaters, and we will be posting when they burst next as quickly as we can, which at the moment, I don't know, it might be a day or two, but eventually we'll try and get that faster. But the point is that if you choose a repeater, you can then go and see, did it burst? You might not know immediately, but it'll be available.
I have a question that maybe Vicky can answer. Is that correct that if we will see the next giant flare from a galactic magnetar now, which it might happen anytime, we will miss the possible FRB again, if any?
Yep. I'm going to pass that to Srihar.
we might detect it in the side lobes of telescopes, but we might throw it out as RFI.
Yeah, we will almost. I mean, unless it happens to be directly in Chime's field of views, right up or something.
No, if it happens to be in Chime's field of view right up, we are more likely to throw it away.
Sure.
Yes, but we know there is. I mean, if you're somehow in the side lobe from the X-ray, we will know there is one. You will look for it.
Yeah.
But
So
let's
what
say
we do is
how
we look
probable it is that it will get somehow in some telescope.
Right. So for Chime, it's hard because most magnetars are in the south. But that said, other telescopes might see it. So I don't know how ASCAP would see a bright FRB which is far out in the side lobes. Probably all the 36 beams will light up, and I don't know what you do with that.
Stare could see it.
Right. Yeah, that's true. Yeah. There is a project called Stare 2. Yeah,
but its sensitivity.
You need a interferometer observing. That's all you need. This
Yeah.
thing is so bright, you don't have to be in pulsar mode. You could be in imaging mode. You just need a interferometer observing above the horizon. That's all.
But the field of view is very small.
Doesn't matter. This thing is so bright, it'll enter through any 100 side lobe. It doesn't
but
matter.
it'll be flagged as bad data. I mean, it will almost certainly be flagged.
But you can go and look at the
go
data. You
back.
just need an interferometer observing. Yeah.
So I mean, are there models where you might get a FRB like minutes or hours after the giant flare, or only like during it and before
it? Make a model, Brian.
Say yes.
Say yes.
Yes. No. Anyone? No. In our models, it'd be at the same time. You mean the giant flare defined by gamma rays or something, or?
Yeah.
Yes,
but I mean, if there's like multiple like closely spaced shells at slightly different speeds that sort of catch up with each other like minutes or hours after or something.
It's usually hard to do that. Things tend to remember more what the central engine is, how long it's active, meaning the millisecond light crossing time. They tend, but I don't know. Maybe others have. Yuri?
But I mean, I just want to note for 1806, I think is Maura still here, or
No,
she got on to 1806 with Parks pretty quickly after the event, like within a few hours, maybe, I can't remember. And so they were in pulsar mode, and I assume that they looked for individual bursts and didn't see anything.
But you have to get really lucky for the rates to even work. There's maybe one FRB per galaxy per century, and if many are repeaters, then actually most galaxies don't have any FRB at all. Or you're lucky and you have one every 2 seconds. So you don't even expect an FRB from one of these sources.
But if we have 30 magnetars and they're all no more than 1,000 years old, then we've got one in our galaxy.
You could expect something much lower in energy than the energy of the FRBs that we've seen in other galaxies.
Okay, let me switch gears a little bit because we have a couple of slides from panel members. Just, talk about.
There's been a fair bit of discussion on these.
How to believe.
Oh, there we go.
Sorry. So I've put up these are the apparently non-repeating, as we call them, right? FRBs that we've from both ASCAP and DSA down here. I've put up from the emission. I think all of them show emission at this stage. That includes, and don't blame Ryan for this, what we're calling preliminary for this one. People have been calling it elliptical. We don't use that word. It for sure shows some emission. TBD whether that's associated with star formation or not. So hold up on that one. This is 180924. They all show emission. That one's several of them. The emission looks unlike star formation, and your galaxy speak. They're called liners, which is a source of hard emission. But what is certainly holding up for a number of these is separations that are quite a few kiloparsecs, 5 kiloparsecs. Localizations well beyond, in this case, and for sure in this case, the bulk of the stars or star-forming regions of those galaxies. So whether or not they are even forming stars, it's clear they're not occurring within the star-forming regions of those galaxies. This one is almost certainly red and dead. Of course, the association's less secure. And this is the one that I was mentioning where we do have a detected source within the localization, but it's very faint. Now those types of sources take considerably more resources to follow up, unlike the rest of the panoplia. And those are at the same redshift and only a few tens of kiloparsecs apart. So there's at least one FRB, an emerging pair of galaxies. In fact, the star formation appears elevated in the host.
to ask, so as Tane pointed out, for the DSA localization, there's certainly room to hide a dwarf galaxy in the foreground in front of S1, which would be possibly more on the bullseye, just like what Wenfei showed before.
That one looks exactly like your before slide.
Exactly. And certainly there's like, I forget now, half a unit of redshift in which you could hide a 121102 style host galaxy and not be able to see it.
Well, we saw the statistics from the first talk, which is that if you go deep enough, you'll definitely see galaxies.
Right. So then, so what does that association mean? And likewise, I could ask the same thing for that last one.
That one's only 23rd magnitude, so it's not quite as you'd have, if you're here, this is already 23rd magnitude, I think. But if you went down to 25th, several magnitudes deeper, you would definitely see galaxies, at least statistically speaking. You should still do that. Yeah, I think the community needs to agree to some extent what constitutes associations. We're gonna have to be careful to what extent we use the DM in those associations was certainly done for the DSA event. And I think it's going to depend a bit on your science interests. When it comes to one of the things that excites me the most is measuring a DMZ relation. There's no way I would ever use a burst like this, where the DM is now figuring into the actual host identification.
But if it's too close to the galaxy, then you've got contamination. So it has to be has to be just right.
I think I'm willing to marginalize over that contamination. That's a it's
a good problem to have.
A good problem.
Not understanding why is it important that if you integrate deep enough, you'll find some dwarf galaxy. I mean, the false positive is set by your radio crosshairs landing on top of an elliptical, because not everywhere you point, you find an elliptical.
That's right.
So that is a secure association.
We're speaking of this one.
Yeah, that's fine in individual cases. But I think if you find a 10 kiloparsec size galaxy, that's a secure association.
Both of the last two figures here
did not land on
the host
Well,
galaxy.
we don't know this redshift yet, so that could actually be pretty close to L star.
Sure, but in principle there could be if you had a deeper image, you would find galaxies that would be potentially better matches, and then you have to rely on the DMZ relationship to sort out which one you want to believe more. But now it's a circular argument to get to the DMZ.
I would not use that case in the DMZ analysis.
Other thoughts on this?
Yeah, the other issue I think that we might have with some of these types of events, if they are sufficiently far enough out and there is some underlying host, we may not even detect it. So I don't know. I think that's something worth thinking about.
I was just looking at this more. You know, a lot of these, as you said, are kind of on the outskirts of their galaxies, may not even have underlying star formation. Is that weird in the magnetar scenario? Because I would expect them to be correlated with young regions.
Almost all the magnetars in our galaxy, which are older, many of them are sitting in molecular clouds and in very, very messy regions, like the most messy regions you can think of.
Right.
The scale height is like 30 parsec above the galactic plane or something.
Only 30 parsec.
It's very, very small.
Yeah. So this already is inconsistent with what you see in the Milky Way, I think.
Or just with expectations, correlations with star formation or something like that. Mm-hmm.
I mean, yeah.
Other ways to make magnetars.
Just
No, I know.
Maybe Chris Thompson's right, and that would be another question. Like,
well,
how could
you could flip that around, right? We could say the same thing about neutron star mergers, right? In GRBs, we see that GRBs are offset. We know that they come from, at least in some cases, from neutron star mergers. But the double neutron stars in our galaxy sit in the galactic plane. So you could do the same kind of, right? Just pointing that out.
I think. Can I make a comment? I think it seems to me that the discussion of the observational strategies should be less tightly connected to a particular model assumption. Unless, I think we should be careful not to switch this. And another comment about there was a question about the afterglows. I think that even in the optimistic case, where this thing emits, let's say, 10 to the 43 ergs it's like 8 orders of magnitude lower energy than GRB energy. So it's even if it does produce afterglows and so on, it would be difficult to see them to a significant distance. So I think you really want to be there on the event itself.
No, but I mean, if you have a FRB which is really close, if you have a FRB which is say localized to M82, and you go there and you see, you should.
If you have something that close, you go every telescope would go and look at
you
it.
throw everything at it,
Okay,
right?
but that's
Yeah.
obvious, of course.
Just to respond to Ben, the difference is that our galactic magnetars are supposedly older than the FRB magnetars, where for the binary neutron stars, they're much younger than the other ones.
Agreed, we are not connecting everything.
Okay, let me. Brian had a few questions that he wanted to talk about. I think related partly to the same issues, but also the use of FRBs as probes. So I don't know, Brian, if you want to expand on that.
Most of it's pretty self-explanatory, but I guess the first question was just to counter Ito's question, which is what more observations should we get? And as I sort of flagged in my talk, I think that we might be starting to lag behind in the tools that we're using. And I don't know if Kendrick wants to comment, because you and Masood have actually written one of the sort of traditional extragalactic astronomy papers and applying this to fast radio burst. Do you think we need a whole new set of tools and calculations and simulations to handle these sort of large-scale structure questions, or we can just copy things over from what we've done with galaxies?
I think mostly there's an established toolkit in cosmology for computing angular cross correlations between catalogs. The only thing that's kind of unique about the FRB case is that it can be difficult to disentangle correlations from propagation effects from correlations due to spatial clustering. So the modeling, the interpretation of the cross correlations may be a little more difficult. You need of order 1,000 FRBs to start getting interesting cross correlations in a wide variety of models, which we have with CHIME. So this is something we're working on now, and hope to have something out soon.
But when you do like a BAO experiment with Sloan, there are these ways of correcting for non-uniform coverage and other selection effects associated with the survey. Those tools aren't directly transferable. How much are you worried in the sort of the analyses that you've done about correcting for incompleteness and sensitivity and other systematic effects?
Yeah, you have to have some prescription for making random catalogs. So like in the CHIME analysis that we're working on, one thing we do is just assume that our exposure is independent of RA at a fixed declination. So we make randoms by taking the FRBs that we observe and keeping the declinations fixed and randomizing the RAs.
Can you just to clarify, when you said 1,000 FRBs, do you mean 1,000 with just FRBs straight up, no localizations, no host associations?
Oh yeah.
Or do you mean 1,000 with all this ancillary information?
Oh no, I'm thinking of a situation where you don't have per object host associations, and so you're trying to establish redshift distribution statistically by cross correlating with a galaxy survey.
Okay. Well, to jump ahead to the third one, in previous FRB conferences, maybe because we didn't have any other data to talk about, there was huge discussions about fluxes and fluences and distributions, and we had a couple of mentions of that, and then we sort of moved on. I'd be curious to hear people's thoughts on, just how much information is there in flux and fluences that we don't already have, and can it be combined in some way with other things like DM?
Yeah. So I think here we should caution the people who are not as familiar with the radio observations that any measurement of flux or fluence is contaminated by the primary beam of the telescope. And since except for interferometric except for interferometric ones. And yes, so if you want a clean sample, you can use just the ASCAP ones as long as they're in excluding the outer ring of the path. You can use the inner beam detections. Otherwise, everywhere else you have to worry about how far out into the primary beam it was detected, and therefore every fluence or flux is a lower limit on the true value.
But if you do have a single power law describing the fluence distribution as they arrive at your telescope, then signal to noise is a pretty good proxy, and it doesn't have these problems. That said, I agree with Vikram's sort of insinuation in the first talk about the log n log s purgatory that we were in for 3 years.
Yeah.
We didn't actually learn very much.
Yeah.
I agree.
That's a polite way of saying what I was asking.
Yeah.
Yeah, Vicky's talk had that terrifying triple detection.
Yeah. Yeah.
And without 2 of those 3 detections, you would have thought, oh, cool, that's here. But the position is potentially off a lot.
Yeah, so the only thing that I didn't show in those plots is that when an FRB is in a very far side lobe, and when it is, well, if it's broadband, it has a very clear spectral signature, so that we can identify with pretty good confidence FRBs that are in the far side lobes and chuck them from the statistical analysis. Now, it will still have some contamination, but it's probably it won't be huge.
Right.
We hope.
Yeah, I would say yes, and that's useful. And the reason why is that we have a DM redshift relation. So flux is going to tell you the luminosity.
There's no beaming.
I think
pseudo-luminosity, yes.
From the GRB, I think experience, like people were doing log n log s modeling. Okay, this didn't prove to be very useful until there were localizations and counterparts, and then things were solved. And I think it probably will be the same here.
Daniele, can you say, like, obviously ASCAP is getting localizations right now, but with the baseband localization system, like in a year or 2's time, like what is the chime sample going to look like in terms of number of localizations and fluxes and all the rest of it?
Localization?
Yeah.
Of course, chime doesn't have the localization capabilities of ASCAP, so we will be having some probably fraction of arc minutes localization. I think it's going to be useful for low DMFRBs to localize a galaxy, nothing inside the galaxy, but still the host. And for far away fast radio burst, we can do what Tara was suggesting, basically correlating with known structures in the universe. Yes, and I think that at the moment we are dumping raw voltages for basically all the chime detections, and I don't think we are 2 years from there. I will more say like I don't know, 4 or 5 months to start localizing with baseband all the FRBs that we get. So we won't have the same localization capabilities, but a very large sample.
But will an FRB that's localized with baseband have a reliable flux?
Well, that's hard. We are working now with holography data, so basically comparing pulsar detection with with chime and with a single dish, and in that way we are modeling our beam, our primary beam. So I think as the work proceeds, at the beginning we will have like fluxes with large uncertainties, and the more time we observe with the single dish, the better these uncertainties will be. Remember that we are well, chime is a cosmological experiment first, and they need to know the beam very well. So we are working with them to, well, our collaboration with the cosmologists will also help us to understand the chime beam well enough. But for that, we will need, I think, a couple of years.
I think like modeling the beam to that level has diminishing returns. I mean, these things are scintillating, so you're only going to measure it to a factor of order unity anyway. So I don't think you should kill yourself trying to model the beam to like 1% or 10% even.
Oh, I'm not. We are making the cosmologists do the work.
Yeah, I'm saying you don't have to wait 2 years to measure fluxes. They are all off by, they are all in error by order unity. No matter, even if you have perfect measurement, they're all scintillating.
I completely agree. I think this is actually the plan for the catalog, and Vicky can correct me. It's like releasing a first version where the flux will have large uncertainties, and then we will improve on that as we improve our beam model.
Vicky, you seem to be hesitating about making a statement.
I'm thinking about your point, actually. We have a very wide band and not a lot of, in other words, the diffraction scintillation bandwidth is very small compared to our band. So if they're band limited, then I see your point. But if they're broadband, then I'm not sure I agree.
And just have a little bit of scattering in the host and it's all off. You can get a broadband scintillation pattern. In the host, you can easily be in the transition between refractive and diffractive scintillation. Entirely possible.
Okay, we have a couple of minutes left. Any other urgent comments that panel members want to make or other questions to address?
Last one?
Yeah.
Big picture question, but we sort of been circling around it. Can the panel comment on whether they think the optimal strategy is to sort of do big surveys in gamma rays, big surveys in X-rays, big surveys in optical, try to cross-match them and do statistics? Or is it really to go after some number very deeply? Because as was pointed out earlier, at the beginning of whichever GRB channel it was, the first 4 were confusing. It took a while before you had a lot. So, I mean, what if we just never find anything, we get bored, we stop doing it? Or for, you know what I mean? Like, there's limited resources and whatnot. So I wonder if you could comment on what people think might actually be the most efficient strategy in terms of finding the multi-wavelength counterparts.
I think possibly one of the most efficient strategies is to actually not try to do a targeted search, but to just look for coincidence observations with the wide field instruments like ZTF, like LAT. You just kind of look after the fact. These instruments that have really wide fields, that way you don't have to ask for time. You just piggyback off of other observations. That might be the least expensive method. Especially because, like in the case of ZTF, it covers the whole sky within a couple hours, so you have a lot of data there to look back on. That's my thought.
I would just comment when the models aren't pinned down or known yet for what could be possible, just a mix of strategies would be useful. So anything from cross-correlating data streams that you get for free, like looking at the Fermi GBM stream, looking at the LIGO stream, cross-correlating both ways, that's very useful and to some extent for free, besides the infrastructure that you have to do to make that happen. And then also these targeted searches too. The FRB event rate is very high, so it's a matter of just kind of putting alerts out there and seeing where various groups' interests lie. I mean, that's the LIGO mode of operation now, at least.
So I agree with Wenfei that I think the field is broad enough that multiple approaches need to be done, and there are certainly enough number of people who are interested in it. My just cautionary note is that don't try to follow every FRB. Be discreet about which one you want to follow. Have a lot of discretion in there.
It's good to cast a wide net when you don't know what you're looking for, but you just have to be cautious about if you find something weird, claiming an association, because there's lots of weird things happening in the universe all the time, and if you don't have any prior probabilities or prior expectations for association, you'll likely get it wrong.
Okay, on that cautionary note. Thank you to the panel members and for everybody for the discussion.